Namaskar, I am Naresh Chandrapant, a professor in the Department of Geology, University of Delhi. Today, we are going to talk about an introduction to crystal chemistry. There are two words in this topic, crystal and chemistry. Crystal refers to a regular internal atomic arrangement of a material which is possessed by most of the minerals, and chemistry refers to the composition or concentration of different elements in the minerals which constitute the rock. As you know, the rock is made up of or is an aggregate of minerals. Now, minerals do not have fixed composition. Most of the minerals have highly variable composition. What controls formation of different crystals, what controls the composition is governed by the nature of the primary nature of the material. So, here we will be talking about what controls the nature of the crystals and how their chemical behavior is something which we can understand. Now, for this, first of all we have to understand the building, a basic building unit, which is either an atom or an ion. So, when we talk of an atom or an ion, it is made up of two main parts, the nucleus and the volume around nucleus. Now, it is very surprising, the nature of behavior of these two parts is very different. The nucleus is a high concentration of mass, whereas the entire volume around it, which is more than 10,000 times that of the nucleus in most cases, is made up of very light particles. For example, the particle which dominantly make up nucleus are protons and neutrons, and the particles which make up the outside volume are known as electrons. The difference in the mass of the two is such that an electron is around 1 by 1837th time that of the proton. So, therefore, one can understand that in a small volume the entire mass is concentrated or large part of the mass is concentrated. The number of positively charged particles which are there in nucleus are known as protons, and their number describes the atom in terms of its atomic number or Z. Besides the protons, there are neutral or non-charged particle of the same mass in the nucleus, they are known as neutrons. The sum of the masses of neutrons and protons make up generally the atomic mass of a particular element. There are situations where the same number of protons are there, but the number of neutrons differ. In those cases, the atomic number of that particular element remains same, but the atomic masses change. In that situation, the different masses are known as isotopes of that element. So, you see, we understand now fundamentally the idea of what constitutes an atom. However, it is not that simple, because how do we define the area or the volume outside nucleus? The reason is that the influence or the charge effect of the nucleus extends up to certain distance, and that distance is known as the radii of that particular particle. If it is an uncharged particle, we call it atomic radii. If it is a charged particle, we call it ionic radii. The range of the sizes which are expressed in angstrom units, 1 angstrom is 10 to the power minus 10 meters, the range varies for, say, let us say hydrogen is 0.46 angstrom for the hydrogen atom to a large atom like cesium, in which case the atomic radii can vary, can go up to 2.72 angstrom. We will later on see that there are other considerations which define this size. So, when we are looking at the atomic radii different from ionic radii. That is, if there is a charged atom, of hydrogen may not have the same atomic radii, as that of atom. It is not only based on the charge, but also on what is around that particular atom or ion, that also changes the atomic radii or ionic radii. Therefore, that is why I mentioned that it is not a very simple measurement which can tell us what is the atomic radii or ionic radii, especially in a compound. So, but it is very important. Let us say take case of a simple atom like a metal, where it is made up of similar atoms. Then if the two similar atoms join to form a compound, then the atomic radii will be half the distance between the centers of the two atoms. That is, the interatomic distance divided by 2 will define the atomic or ionic radii of that particular type of compound. However, there are many compounds which are significantly different. So, we come to the question of how the different atoms come together or are glued together to form a compound, which in case of geological material we call as minerals, which may be very complex. The gluing together or joining together of different atoms is on account of the outer electrons in an atom or an ion. These outer atoms are called as valence electrons, and for crystal chemical considerations, the valence electrons are most important or are very significant. Now, it is not that the valence electrons occur similarly in different compounds or different elements. Also, there can be a situation, or why should valence electron be transferred to another atom to form a compound? The reason that the valence electrons transfer to other atoms is to acquire a stable configuration. The most stable configuration is where, following the rules of the distribution of electrons, the structure is complete. That means, the distribution of electrons is distributed to its fullest in different shells. For example, in K shell there are 2 electrons which is defined as 1s2. Now, if there is a subsequent shell, then there will be 2s2, that is 2 electrons in the first shell of the second shell, and 6 electrons in the subsequent one. So, 2s2, 2p6. Now, if there is a third shell, it will be 3s2, 3p6 for a stable configuration. So, therefore, if there is an atom which has 1 electron in its outermost orbital, it will tend to shed that, and it may go to another atom, where that can lead to formation of the stable configuration. So, if that situation exists, that will lead to joining of the 2 atoms together and formation of a stable compound, like one of the best examples of this can be from sodium chloride. I will just illustrate this. we can look at say sodium and chlorine, and we can first in a simplified way consider them spheres of opposite polarities. Now, if both are surrounded by similar number of atoms or ions, that is this is also surrounded by 6 atoms and ions, and this is also surrounded by 6 atoms and ion, then the influence, outside influence is similar. And if their ionic radii or atomic radii are similar, then the opposite polarity spheres, the half the distance will constitute the ionic radii. In this particular case, the kind of bond which is there is because of the opposite polarity. So, this is known as ionic bond. This is achieved when we look at the configuration of electrons in the two cases. In case of sodium, the configuration is of this nature, that is the first shell 2 electrons, the second 2 electrons in the first orbital, and then 6 electrons in the outer orbital of the second shell, and as we start with the third shell, 1 electron in the S or the first shell. A stable configuration can be achieved if this valence electrons can be contributed to something else. When we look at the chlorine, this will represent a stable configuration of neon. When we look at chlorine and write the same distribution of electrons, then it will be and as you can see, there is scope of having 1 electrons which will make it a stable argon distribution. So, therefore, this 1 electron goes or is shared by the structure of the chlorine, and that makes it, since 1 negative charge is going, that makes it positively charged, and since 1 electron is getting added here, it makes it negatively charged. And when the opposite polarity charge is thus distributed, since this is positively negatively charged, they are bonded together because of the opposite charges, and this kind of bond is called as ionic bond. We will later on see that none of the bond is of a n member or of a fixed type. Actually, the bonds are certain percentages of ionic bond and certain percentages of other types of bond, which we will subsequently be looking at. In this case, it is simpler to work out what are the ionic radii, but in cases where the radii of the two elements which are bound together are significantly different. Let us take the case of magnesium and oxygen. The radii are significantly different. In that case, if we know or if we can work out the interatomic distance of the compound, that is MgO, we can subtract, let us say, if we know the bond length of or the ionic radii of oxygen, we can subtract that, and that will give us the ionic radii of magnesium. However, there are complications. The complication is that there is no fixed ratio or radii of oxygen. It can vary from 1.35 to 1.42 angstrom depending upon how many other oxygens are around it. That is, if it is in two-fold coordination, the atomic radii of oxygen is 1.35 angstrom. If it is in 8-fold coordination, it changes to 1.42 angstrom. So, therefore, it is a function of how many other cations or anions are around a particular atom, and this is true also of the, this is not only true of the anions, but is also true of the cations. Similarly, for potassium also the ionic radii varies depending upon what is the coordination or what are the other atoms or anions are around potassium. So, therefore, the nature of bond, nature of ionic bond depends upon achievement of a stable configuration, and this is a prime example. Now, we will look at properties of material which arises out of these bonds or the distance of the bonds. If the distance of the bond is such that it is short, that is the opposite polarity charges centers are closer together, it will be difficult to break it. If the distances are large, it will be easier to break it. In case of, let us say, these compounds only, if we see this as a plot of the bond lengths and the temperature at which the compound melts, that will be a good example. So, let us look at this relationship. The force which keeps the ionic bond together can be defined as a constant K and multiplication of the positive and negative charges divided by the square of the distance between the center of the two atoms, and this is also known as Coulomb's law. But as I said, a graphic illustration of this we see in this diagram. This diagram has the horizontal axis as the distance between the center of the positive and the negative charges. So, this is basically the bond distance expressed in angstrom unit, and it is about 0 to 4 angstrom. And the vertical axis is the temperature at which the compound melts. So, let us say it is up to 0 to 1000 degree centigrade. And if we plot now the different sodium and sodium iodide, sodium fluoride, sodium chloride, sodium bromide compounds, then they plot in this form NaBr, NaCl, NaF and NaI. And as you can see that with the decreasing interatomic distance or the distance between the center, the melting temperature is higher, it is increasing in this direction. So, therefore, it is difficult to break the bond as if the distances are shorter, and that is expressed by Coulomb's law. So, this is the nature of the ionic bond. This leads to a moderate hardness and a moderate strength of the compounds which are largely governed by ionic bond. The other type of bond which is there is vastly different from ionic bond, in that the electrons do not achieve stable configuration by the type of stable structure which we saw previously. The electrons are actually free, they are unattached. That type of bond is known as metallic bond. You will see in the figure, so on account of infinite spacing between elements in the case of metallic bond, there is the discrete bonding orbitals distance changes in case of metallic bond, and the energy occurs in bands, and this actually leads to band theory. So, in metallic bonds there are some bands which supply the electrons, those are known as valence bands, and there are others to which the electrons migrate because the electrons are unattached, and to the bands to which the electrons migrate are known as conduction bands. The highest energy level of the band at low temperature is known as Fermi level. It has very important bearing on the nature of the metals. That is, if the valence bands and the conduction bands are vastly separated, that is, if we take this axis as energy axis and the valence bond and the conduction bands, one example of valence and conduction band in the same element is magnesium, in which the 3s band is the valence band and 3p band is the conduction band. So, if there is a significant separation of the energy levels between the two, the nature of the atom is such that they are insulators. If this separation is less, then they act as semiconductors, and if the valence and the conductance band overlap partially like this, then these elements actually act as conductors. So, as you can see, the way the internal atomic arrangement and the way the compounds are bound together defines the intrinsic property of the material, and that leads to the definition or control of the intrinsic property of the crystal. As you in most cases of the metals, the situation is that of a conductor, that is, the valence band and the conduction bands overlap. So, therefore, they are very good conductors, and we know the example that copper, aluminum, etc., are very good conductors of electricity. Now, when we have these properties, these two extreme types of bond, in between we have another type of bond which shares the space between these two bonds. As I mentioned earlier, there is no natural mineral in which only one type of bond exists. We will see a derivative of some of these bonds also. The bond which is in between the ionic and the metallic bond is known as covalent bond. Now, in case of covalent bond, the sharing, the stable configuration is achieved not by migration of the electron, but by sharing of the electron. If the sharing of the electrons lead to achievement of stable configuration like that of the inert gases, that kind of bond is known as the covalent bond. And because it is the electrons which are shared by the two different atoms, the bond strength is very high. So, we saw earlier the structure of chlorine. Now, we see chlorine is a highly reactive element, but we will see that by a kind of bonding it becomes very stable. We learned earlier that the third shell of chlorine has this configuration 3p5, that is 5 electrons. Now, if we combine chlorine which has 5 electrons around it. If we combine 2 chlorine and this electron is shared, then the p subshell will behave in this manner. These two are shared, and now you see that the combined chlorine 2 has a stable configuration of 6 on either side, which is the stable structure for p shell. So, therefore, a highly reactive element like chlorine can become stable by a covalent type of bond, and this is a perfect example of a covalent bond. This bond, because of the sharing involved, leads to very strong bond strength, and the example of this in the natural sample is exemplified by diamond, which has the highest hardness amongst the naturally occurring material and significantly higher than any other known naturally occurring mineral, just because of this bonding. After discussing these 3 types of bond, we will look at some other bonds which result as a function of the nature of the binding material. For this, we will first learn the concept of electronegativity. This property is basically the capacity or the nature of an atom either to accept or to donate an electron. How this is there, that the electronegativity controls the nature of bond, can be seen in this diagram, where the vertical axis is the percent of ionic bond and the horizontal axis is the difference of the electronegativity of the elements which are joined together as bond. So, this is the difference in electronegativity. Now, in this, the graph is not a straight line, but on more or less straight line for different compounds, and this means 0% ionic bond and this means 100% ionic bond. We see in the diagram, as you can see, that different compounds plot in this fashion along this line, which means that most of the compounds have certain percent of ionic bond as a function of the difference of electronegativity. That means also that we do not have a 100% ionic bond or a 0% ionic bond, which means that most of the bonds are hybrid bonds. This is what is very necessary to understand, that most of the bonds are hybrid bonds. Now, in bonding, what happens is that there is often a polarity which develops in bonding. The polarity means that even though the compound is electrically neutral, it has a positive charge on one side and a negative charge on other side. Now, if such a situation is there, then the positive charge on one side will apply or will attract a negative charge on other side. This leads to certain weak category of bonds. One of the weak category of such bond is known as van der Waals bond, which is on account of a polarity developed within a mineral. Since these are weak bonds, so they are planes along which the elements separate easily. So, they are often known as the cleavage planes. The famous basal plane cleavage of micas or phyllosilicates is a result of the van der Waals bond, and this is true in many other minerals. So, we see that it is important to understand the crystal chemistry, because the behavior of the compounds which we call as minerals, which constitute the rock, is guided by the nature of the elementary particles. The properties of the mineral is totally dependent upon these constituent particles. Therefore, an understanding of crystal chemistry is a necessary requirement for understanding the minerals and the rocks. Thank you.